This DeBacco University video is going to walk you through the steps it takes for writing electron configurations and also orbital notations. It might look a little confusing here right above me, looking for boron, looking at the electron configuration, the orbital diagram. I'm going to walk you through some of these steps that hopefully you'll find easy to follow, so you yourself will be able to write electron configurations and orbital notations. All right, the goal of this slideshow is going to have a lot of transitions. Look in the description for those who have developed some of these slides. I've kind of modified some of them to hopefully make it a little easier to understand through this process. So looking at the first one here, the first energy level is comprised of just one sublevel. Then we go through and we progress. It's called the 1s sublevel, and it contains only one orbital, and we see that depicted right here. The second level is made up of two sublevels, and the 2s sublevel and the 2p sublevel, which contains three orbitals. And we can see that right here with those boxes. Any guess about the third energy level? Well, as you might be able to guess, the third is made up of three sublevels, and you see a pattern kind of developing here. And then as we progress here, also notice the sublevels start to overlap, where it gets a little bit more confusing, but we can see at least this natural progression as we're starting with our lowest energy and working our way up from there. The 4s is actually, if we look at right here, actually a little lower than the 3d. This overlap is a very important note when we're going through and keeping track of the order as we make our electron configurations and orbital notations. So we go through and we start with that 1s, and we kind of progress up to 2s, and then 2p to 3s, 3p to 4s, and continue to progress going up in that way. Now the reason why it progresses in this way is that we have to be careful, because as we saw with that 4s is a lower energy level than the 3d, so the 4s will be filled before the 3D. So following this alpha principle really helps keep things nice, neat, and organized. Now the blocks on the periodic table, just as a little refresher, we've got our S block, our D block, which is our transition metals, our P block, and then our F block. Just remember, helium is part of the S block here. And if we're looking at the valence electrons here, of our periodic table of elements, here's our list of elements and the proper configurations for those valence electrons we can see evident right here. So yes, this is important to have the very last one denoted properly, but how do we get there? We're kind of building up and counting as we progress to that element that we're looking at. So again, just here's the elements, and then here's the electron configuration for the valence electrons for those elements. So let's go through some examples here, starting with hydrogen and moving over then to helium. So as we go through, we're not going to go through the periods 1 through 7. Remember, we do have those there, and those periods correspond with the energy levels. Designate the 4 distinct rectangular blocks, the type of S block, a P block, a D, or an F. And as we go through, there's the S block, the D block, the P block, and the F, just like I showed you in the previous slide. Lastly, the number in groups within each block. So we're kind of building from there as well. Remember, there are 2 families in the S block, a total of 10 families in the D block, 6 in the P block, and 14 in the F block. So how do we go about indicating what these are, and where do we put those arrows in these particular blocks? So I'm going to walk you through a couple examples, and hopefully you'll start to see that pattern develop. So here we're starting with hydrogen, 1s1, and it's got 1 arrow. Very simple. Nice way to start. We moved helium over to make it a little easier, but so as we're looking at here, that's where hydrogen is. Now we're going to helium. We're going to move that one over. 1s2, we have 2 arrows. And as we're going from helium, we're progressing to the next element here. We moved helium over. We're progressing to lithium. So we're having to account for all of the previous electrons, but we're building on that. Lithium is located right here in the periodic table, and that's a 2s1 essentially. We see that denoted right here. And then there's our lithium, beryllium. We're just going to start to flip through these, and hopefully you start to see some of the patterns develop, but we have to go over now from the S block now to this P block. So keep that in mind. That are for our boron, we're now at the 2p1, and we're progressing from there to carbon, And then from carbon, we're going to nitrogen. Now notice we put one electron in each orbital. We didn't start to double stack the boxes yet. Now that each one has one, now we go back through and we put the down arrows for the corresponding elements as we progress to oxygen, and then from oxygen to fluorine, and from fluorine to neon. Neon being a noble gas, very stable. We can see why that is. All the boxes are full. As we're going through our other elements here, hopefully you can start to see this pattern progress and continue as we're working our way up, filling up those electrons. Here's our manganese. Again, we see first all arrows going up, and then we follow up with arrows going down as we're going through our corresponding elements. So hopefully this visual does help you kind of understand this a little bit better. So the pattern for reading electron configurations right off the periodic table, essentially there's our 1s2, there's our 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. You can kind of see hopefully the pattern developing as we go about this periodic table. Remember, we do break down, go down to this F block here. If you know 57 to 72, where are those elements? They're down here. A lot of times we break that periodic table and put those groups a little bit lower, come back up here and work our way through that periodic table. If you're wanting to write the electron configuration for any element, just follow this pattern. Remember to stop at the element you are representing or the question that's being asked of you. So for example, chlorine, which is number 17 here, it's got 17 protons. How do we go about doing that? Well, we just kind of keep going through, progressing until we get there. Now we stop at the 3p5 because argon would be 3p6. So we see that buildup, follow that periodic table. This is why it's very important to become familiar with that periodic table of elements. You can also use a shortcut method where you're using neon in brackets, which is a noble gas, and that basically represents all of the previous electron configurations, and you're simply building from that noble gas, continuing until you get to your element that you've been asked about. So what about nickel? It's number 28. It's located right here on the periodic table. Well, we do the same pattern, building up there and getting to 3d8 ultimately there. So here's our kind of progression. And we use argon as the noble gas configuration because we put the brackets there because that's the closest noble gas, and we build from there. Last one, bismuth down here, Bi, number 83. Again, the same thing. It just takes a little bit longer to get there, a little bit more complicated, sometimes a little bit more scary. Don't forget about that F block down there, and we would end in the 6p3 category. And there's a shortcut with a xenon there as the noble gas. So again, as we're going through and progressing, as a reminder of those steps, find the symbol of the element, write the symbol in brackets next to the nearest noble gas, write the outer electron configuration for the remaining electrons. So again, this kind of progression here, here's just a summary of the noble gas notation. Noble gas notation, also known as abbreviation or shorthand for the electron configuration. The noble gas symbol is placed in brackets, followed by the remaining electron configuration. It focuses on the electrons beyond the noble gas core and is very helpful for larger atoms. And here's just kind of showing you the example. Remember, orbitals are not literally empty boxes in a line. Instead, they're specific three-dimensional shapes. They're those probability clouds that show where you're most likely to find the electron around that nucleus. The S sublevel is that spherical shape. As they get larger and larger, they move to higher energy levels. P gets a little bit more complicated, looks a little bit more like that dumbbell-shaped, peanut-shaped. And within the 2p sublevel, there are three orbitals are oriented at right angles to one another. And then they're referred as the 2p, in this example, X, Y, and Z, representing those three planes in three-dimensional space. And they all fit together in nucleus. They kind of look like this. When you kind of look at them, it's a little harder to show on the diagrams here. This is the order in which they were introduced to you, essentially. And as we see that natural progression, we're seeing that build up and that complexity increase. There are plenty more, but they go off screen, so I'm not going to worry about them. We're going to focus on these because if you understand those, you can then work up higher and higher energy levels. But the pattern does repeat itself. Remember this helpful table, as hopefully that will start to allow you to be able to keep yourself organized, because it doesn't go just 1, 2, 3, 4, 5, 6, 7. following this pattern can be very helpful to ensure you're staying nice and organized. So hopefully this is helpful, while a little confusing, to review as you go through and write your own electron configurations and orbital diagrams.